Now let's have a look at the different physical properties of carboxylic acid and carboxylic acid derivatives. So let's start off with the boiling point. First, I would like to remind you of they all have carbonyl group, and the carbonyl group is polar. So there is always a dipole-dipole interaction. This is why their melting and boiling point will be a bit higher compared to their alkane counterpart, which are completely nonpolar. I would like to remind you that for acids, there is an OH group, and the OH group can take part in hydrogen bonding. So let's have a look at the trend here. So the alkane is the one at the bottom. This is for boiling point, and it's quite low boiling point. Close to it is the acid chloride. So it's the boiling point of acid chloride is very close to the alkanes. This is followed by the ester, which is more or less like the alkane as well. So there is not a huge difference in the um, boiling point for acid chloride alkane and for the methyl ester, because even the dipole moment that is created, it's actually abolished by the long chain of the carbonyl when have a long chain of a long alkyl chain. Then you find that the alcohols, then nitrile, then the acid. The acids have a bit higher boiling point compared to their alcohol counterparts. And then the one that stands out are the amides. The amides have high boiling points compared to the all other acid derivatives. This is because there is, as we said, there is the lone pair of electrons on the nitrogen of the amide will take part in resonance that will create a negative charge on the oxygen and a positive charge of the nitrogen. So the dipole moment here is very, very strong compared to the other ones which have only a partial charge. So there's a strong electrostatic interaction between these bonds for different amides. This is why amides, because of the strong electrostatic interaction compared to the other dipole moments that are created for other carbonyl compounds, the amides have high boiling points. So they have very strong attraction. The primary amides are the highest. This is followed by the secondary amides and then the tertiary amides. Looking at the melting points again, they have the same trend for amides like the boiling point. So the primary amides will have the highest boiling point, followed by the secondary and then the tertiary. You may ask why, or may think why the primary will have higher than the secondary than the tertiary. Again, let's have a look. If you have a positive charge on the nitrogen, this moves here with the resonance, and a negative charge on the oxygen. Then if you have a methyl group or alkyl group, they have electron donating property. That means it will reduce the positive charge on the nitrogen. And if it reduces the positive charge on the nitrogen, that means the electrostatic interaction will be less. So this is why when you have two alkyl groups here, both have the electron donating properties, then the positive charge on the nitrogen will be reduced compared to the primary amide. This is why primary amides have higher boiling points than secondary, which has higher than tertiary. Now let's look at solubility. So we know that they have carbonyl group, and the carbonyl group can take part in hydrogen bonding with the water. So first of all, acid chloride and acid anhydride are very, very reactive. And they do not just make hydrogen bonding with water, but they actually react with water. So avoid, when you are dealing with acid chloride or acid anhydride, avoid the use of water completely, because once you add water to acid chloride or acid anhydride, they will react and they will give you the corresponding acid. So you will no longer have the acid chloride or acid anhydride. It's very well known that the acid derivatives are used as polar solvents. So esters, tertiary amides, and nitriles are good polar solvents. Examples of these solvents, the one that most commonly used in organic reactions are ethyl acetate. So we all know ethyl acetate, so it's acetic acid, and then ethyl group. So it's ethyl acetate. This is a very common acid. It's an ester. We have the dimethylformamide. This is a tertiary amide. So how we draw the dimethylformamide? So formic acid has only one carbon, and then we replace it with the nitrogen, and it's dimethyl. So the nitrogen has two methyl group. So this is called dimethylformamide. We usually refer to it as DMF, and it's one of the most commonly used solvents in organic reactions. We also call it N,N-dimethylformamide. The other one is acetonitrile. So acetonitrile is CH3C triple bond O. So it's coming from acetic acid. So we call it acetonitrile. Moving on to talk about the acid-base properties of carboxylic acid, we have learned before that carboxylic acids are weak acid. They can dissociate in water to give the hydronium ion and give the carboxylate anion. The carboxylate anion is stabilized by resonance. So the base here that is formed, the conjugate base, is a very weak base because it's stabilized. So it's a weak base because it's stabilized by the resonance. This is why the acids are, they are weak acids, but they are stronger acids than alcohols. Because we said before, when we talked about the stability of the conjugate bases and the strengths of the conjugate base, the more the stable the base, the less its basicity. And we know that the RCO with a negative charge, the conjugate base that come from the alcohol is actually less stable than the carboxylate one, and so it's more basic. So the alcohols are less acidic or weaker acids than the carboxylic acids. Let's have a look at the influence of substituents on the acidity of carboxylic acid. So the parent acid we will talk about is the acetic acid, because the acetic acid is the one that has only one methyl group and then the carboxylic acid group. So acetic acid, the pKa of acetic acid is 4.8. It's a weak acid because we said anything above 4 is weak acid. Now let's have a look at the second one, which has chloroacetic acid. We have a chloro derivative here on the carbon of the on the second carbon, or on the carbon that is adjacent to the carboxylic acid group. This, if you look at the pKa, you find it's 2.9, which means it's a stronger acid. Why do you think it's a stronger acid? Now, we know that chloride has its high electronegativity. It's more electronegative than the carbon. It has an electron withdrawing property, so it will attract electron towards it away from this carbon. And if we attract the electron this way, that will even stabilize the carboxylate anion that's formed even more, make it even less basic. That means that the acid that comes from the conjugate base is going to be a stronger acid. So when you have the conjugate base here, so it's Cl, hydrogen, hydrogen, and C double bond O, O. There is a negative charge, and now because the chloride has an electron withdrawing property, it will reduce the negative charge on the carboxylate anion. So the carboxylate anion not only will be not only stabilized by the resonance, but also by the negative inductive effect, or the electron withdrawing property of the chloride. This is why when we add 2 chloride, then we have even more stabilization. So the acetic acid will be 1.5 pKa, 1.5, so it's even a stronger acid. If we have 3 chloro, it's 0.7. This is a strong acid, trichloroacetic acid. So what about if we add alkyl group? So when we have something like propionic acid, which is the following acid after the acetic, so we replace one of these hydrogens in the acetic with amethyl. We know that amethyl group have an electron donating property, so it will destabilize the carboxylate anion. The destabilization here will not be very high, so the difference is not massive. So, but it's still a weaker acid than the acetic acid. If we have a chloro derivative again from propionic, it will exert the same effect like the chloro on the acetic acid. So alpha chloropropionic acid, and we said alpha because this carbon can be called alpha and this is beta, so we can call it alpha chloropropionic acid. Now the pKa is still slightly less than the chloroacetic acid, so it's slightly more acidic. And then if we have the chloro then more further away, so it's on the beta one, you'll see that the acidity here is less. Why? Because the inductive effect is less effective as we go further away from the functional group. So here this chloro group will have less effect on the stabilization of the carboxylate anion that is formed, or the conjugate base, compared to this chlor, which is on the alpha carbon, because it's more further away from the carboxylate anion. This is why the here when we placed it one carbon further, the acidity reduced again.